Yeah.
Or okay, maybe I can just not use the pointer. Yeah.
Okay. Oh, now I see your cursor moving a little. Oh wait, it stopped moving, but it was moving for a little bit.
So now you cannot see it.
It stopped moving. Wait, try moving it one more time. Okay, yeah. It's for some reason it stops moving when the presentation is actually when the presentation is like presenting. If you take it out of presentation mode, I can see the mouse moving.
Yeah, I see. Yeah. Yeah, maybe let me just not use the presentation mode.
Okay, that's fine. Yeah, we can see it moving now.
Yeah, let's see. Let me try to enlarge this slide as much as possible. So can you see it now? The cursor, the mouse, and the slide?
Yes.
Okay. Yeah, let's just do this. Okay, so there are many major advances in the history of wireless, including FM radio, which is still being used today, and television broadcast that is also being used today. And more recently, we have cellular communications and wireless local networking, which is actually Wi-Fi. So these two technologies have been dominating nowadays. So I believe every one of you is using it in some way, and every day, every time, almost every time. Right? So for example, now I believe each of you is connected to the internet in this Zoom meeting using either cellular or Wi-Fi. Okay. So what are the benefits of wireless technology? Why do we use it so much and so ubiquitously, so widely, right? So the primary advantage of wireless is its mobility. So it allows devices to really move around anywhere you want, right? So that's why we are using wireless technology so widely. And even there are several challenges and disadvantages of wireless, as I will discuss shortly. We still use wireless technology so widely. And the primary reason is because of its mobility. And another important benefit of wireless is it does not need any deployment of cables, right? So this is really important to provide internet access to rural areas, okay? For example, Facebook has a project which is to deliver internet access using a drone, which is staying in the air, to working as a base station or access point to provide internet access to a large rural area, such as in Africa. Okay, so in this case, it's really not economic or even infeasible to deploy cables to connect devices to the internet. Okay, and another benefit of wireless is that the deployment, because we don't need any cables, the deployment is much faster than the wired services. And this feature is very important in some applications, such as in disaster recovery. Right? For example, after a hurricane, we have no infrastructure, we have no cables, right? At that time is money. So it's really important and critical to deploy a wireless network, which can happen very quickly. And another application of another use case is the battlefield, where we need to deploy wireless network very quickly. So on the other hand, there are several challenges for wireless technology. Okay. the first one is reliability. So due to the mobility of wireless devices and due to the complexity of the physical environment where wireless signals propagate through, it's very hard to guarantee reliable wireless connection. Okay, sometimes when you are indoors, you may have a very poor cellular signal, right? You may have a good Wi-Fi signal, but typically the cellular signal is much worse than when you are outdoor, right? So it's really difficult to guarantee a reliable wireless connection. And this is different, totally different if you use a cable to connect to a device, right? If you have a cable, then as long as your device is connected by the cable, your connection speed is very reliable, very stable. So another disadvantage of wireless is the energy consumption is typically higher than when you use a wired connection. Okay, so I believe each of you has to charge your iPhone every day, charge your phone every day, right? Because of the energy consumption. And due to energy consumption, the transmission range of a wireless device is also limited. And another important challenge for wireless technology is the interference. Okay. So because wireless signals can propagate in different directions, okay, it can generate interference to unintended devices. Okay. When your device emits some wireless signal, it can be picked up by other unintended devices, which cause interference. So in order to avoid interference, we need different wireless devices or different wireless technologies to use different frequency bands. As a result, each technology is allocated some bandwidth to use. So this figure shows the frequency allocation in the United States, where you can see all the colorful blocks represent frequency bands which have already been exclusively allocated for some technology or for some wireless service. So it's really hard to find any white blocks in this figure, which represent unoccupied or unallocated frequency bands. And another major challenge for wireless is because wireless devices are mobile devices, portable devices, they are very limited in several dimensions. So it has a battery, which is limited, and also the size and the weight of the device are also limited. And this can really cause challenges for wireless communication. So let's look at, so by the way, Brittany, do I have 15 minutes for my talk?
15 minutes. 15 minutes. 50. Yes, sir. Yes, sir. You do.
Okay, I will try to keep it in time. Okay.
Oh, you're good. Take us. Yeah, you're good. But yes. Okay.
Okay. Yeah. So let's take a look at wireless channels. How does the physical environment change the wireless signals propagating in the environment? Okay. This greatly determines the characteristics of wireless connections. So the good news is that in wireless environment, we don't need a direct signal pass, which is called line of sight from the transmitter to the receiver. So ideally, a line of sight signal pass is best, but that is not required. Because we have different propagation mechanisms, which can cause signals to arrive at the receiver along different paths. For example, we have reflection, we have scattering, and a diffraction of the signal. So as you can see in this figure, signals can arrive in different passes, right? So we don't need a direct pass between transmitter and receiver. And also some signals can propagate through some object, okay? However, there are also substantial challenges for wireless channels. The main challenge is called the multipass effect, which means multiple copies of the same signal can arrive in different paths at the receiver. Okay, so this often degrades the received signal, making it more difficult to correctly decode. And other challenges for wireless channels include interference, which is due to the broadcast nature of wireless signals, as I just mentioned. And also noise can be a concern. And actually noise is a concern for both wireless and wired communications. And the Doppler effect is a feature of wireless channel. So we know the signal frequency can change when devices are moving. So that is called the Doppler effect. Okay, if we have a wired connection, we would not see Doppler effect. Okay, let's take a look at the recent trend of wireless technology. So as we know, in the past 10 years, we have seen explosive growth of wireless traffic. So roughly after the first iPhone was introduced, we have seen a great increase in wireless traffic. And that is mainly due to a wide variety of services and applications which are made possible on our smartphone, right? So nowadays we have so many apps on our phone. And also nowadays, so actually the data traffic has grown by a fold of more than 1,000 since 2010. Okay, that's a 1,000-fold increase in wireless data traffic. And most of this traffic is from videos nowadays. As we know, we usually stream a YouTube video on our smartphone, right? And another reason why we have so much wireless traffic today is we have even more mobile devices than the number of people on the earth. Okay, in the past, maybe around the 2000s, no one has a smartphone, but nowadays everyone has a smartphone, right? And in the future, we will have even more smart devices like a smart glass or smart watch, right? All these wireless devices will generate wireless traffic. Okay, so why we have so much wireless traffic nowadays, right? So the essential reason is because our smartphones are much more powerful than it was before. Okay, so in the past, we only used our phone to make a voice call, right? To call someone or receive a call. But nowadays, it has so many functions, right? So if you look at these advertisements from Circuit City in 1990, so Circuit City is an electronic retailer like Best Buy, which does not exist nowadays. So here, this advertisement includes a wide variety of devices, like a desktop computer, like a landline telephone, like a hard drive, like this DVD player or cassette player, right? And a radio player. And this is a video recorder. All these devices nowadays can be all these devices are actually integrated in a single iPhone nowadays, right? A single smartphone. And also nowadays, the most recent version of iPhone 13, is millions of times more powerful than the computer used in the first moon landing back in 1969. Okay, that computer was the most powerful computer at that time. But now it's our iPhone is just million times more powerful than that. And also mobile phone users use these devices heavily every day. So all these reasons are why nowadays we have so much wireless traffic. So we can understand why we have such large wireless traffic nowadays. So this is essentially because of the interactive driving forces between wireless service, wireless traffic, and wireless technology. Okay, so when we have a better wireless technology, which means we can transmit more data, then we will see more new services and applications on wireless devices, right? Such as Uber, such as Lyft, such ride-sharing services, they were not there before. Okay, but then they were made possible because our smartphones can track our positions and it can keep us connected no matter where we are. Right. So these advances in wireless technology really enables these new services and applications. And on the other hand, when we have new services and applications, it will generate more traffic on these wireless devices. So it's really the interactions between these three driving forces, which result in the advances and the revolution of wireless technology and the services. So let's take a look at a particular wireless technology, which is cellular networks. So this is arguably the most important and prominent wireless technology in use nowadays. So everyone with a smartphone is connected in the cellular network. So the goal of this cellular technology is to provide a seamless coverage over wide geographic areas. So that means no matter where we are, we should be covered by a cellular network. Okay. So cellular technology also has a long history. Okay, we had different generations for cellular technology. So if we compare this earlier generations from 1G through 4G, we can see that, okay, 1G started to enable voice communication, okay, and then 2G can outperform 1G by providing better voice communication, okay. But at that time, we can only use cellular to make voice calls, okay. But then starting from 3G, it provides data communications, right? We can use 3G to browse websites, right? But then in 4G, it provides even better data communications, as we can use 4G to stream YouTube videos. Right? But nowadays, we are starting to use 5G. Okay, 5G has not been fully deployed, but has been deployed in some areas. So what's new about 5G compared to the early generations is that besides increased mobile data rate, we have new use cases, which is called ultra high reliability and low latency. Okay. So ultra high reliability really means that we want to improve the reliability of wireless connections and also reduce the latency of wireless connections. On the other hand, another new use case is called massive machine type communication. That is to enable a large number of machines like sensors or other devices to be connected in the cellular network. So these new use cases really enable new application for 5G. So people envision that 5G will enable, after 5G is fully deployed and mature, 5G will enable remote control of things. Okay, so these things include not just mobile phones, laptops, but also general physical objects like our machines, for example, our appliances at home, right? And maybe manufacturing machines in factories. So all these things will be connected in 5G. And then 5G will allow us to remotely control and monitor these things. And for 6G, people envision that, so the research and development of 6G has already begun. Okay, and 6G is envisioned to provide even better remote control of these things. So, so cellular technology is not the only wireless technology in wide use today. So as we know, Wi-Fi is another widely used wireless technology. So different from cellular, Wi-Fi aims to provide coverage over local areas. So it aims to cover hotspot areas like a home, office, or shopping mall or airports. So compared to cellular, Wi-Fi can provide higher throughputs, but within a smaller coverage areas. So in some sense, Wi-Fi is complementary to cellular. So typically, when we are indoors, we have Wi-Fi connection, which allow us to access the internet. And when we are outdoor, when we are on the road, we would be connected by cellular. So no matter whether we use cellular or Wi-Fi, the future telecommunication network will connect a wide variety of things, not just portable mobile devices operated and carried by human beings, but also any physical object that we can think of, right? Including sensors, including appliances, including machines working in a factory, including maybe animals, right? So this is called the Internet of Things, okay? And this will be enabled by not just 5G, but also future Wi-Fi technologies. So thanks to the Internet of Things, it will support real-time remote control of many physical objects, right? And this will enable a high level of automation, right? So imagine, for example, in a farm field, we may deploy sensors to monitor the temperature of crops, right? So we can monitor the temperature remotely using the Internet of Things, and then we can make make smart decisions based on that information. For example, if the temperature is too high, then our irrigation system can automatically water the crops, to water the field, farm field, right? So this automation is only possible with this Internet of Things, which enable real-time remote control. So IoT also has wide applications, including transportation, agriculture, and manufacturing. So for example, one application in manufacturing on factory floors is that we can use sensors such as a camera to monitor the quality of the product that is being manufactured. Okay, and this will allow us to remotely and automatically control the manufacturing process. Okay, for future wireless networks, people envision that we will see a convergence of different wireless access technologies, including cellular and Wi-Fi. So in the future, the boundary between cellular and Wi-Fi will be blurred in the sense that we don't care which specific technology we use. We just care about we have wireless access to the internet, no matter where we are. And also, we aim to provide better network coverage, especially in rural areas. Okay, so that can be improved using satellite communications. And one big difference for future wireless networks is that it will be more open and programmable to support diverse and innovative use cases. So in current wireless networks, it's kind of closed and inflexible in the sense that you cannot change the network much. But in the future, it will be much more flexible. And for wireless networks, in terms of spectrum usage and frequency bands, we will use higher frequency bands, which are more unoccupied. So another important trend, which we will elaborate in the following, is that we have more and more computation-intensive services and applications running on top of wireless networks. So this means that we will see, we actually have already seen a convergence, and we'll continue to see this trend, which is the convergence of communication and computation. So we already have some emerging video applications, such as virtual reality, augmented reality, or 3D video, or panoramic video, which are very computation intensive. Right? So as example, when you play a computer video game, your device, either a smartphone or a laptop, will be very hot, right? And the fan will be working all the time. So that indicates that this service, this application is very computation intensive. And besides these video applications, we have emerging machine learning and AI applications, which are also computation intensive. And I will discuss machine learning and AI in more detail. So traditionally and currently, we usually push most of the computing and the storage functions to the cloud in data centers. Okay, so as we know, big IT companies like Google, Facebook, Amazon, they have their own data centers with a large number of powerful computer clusters of computers. So this cloud computing paradigm has been very successful and being widely used in practice. And the main benefit of cloud computing is that it virtually provides unlimited computing and storage resources, right? So we can throw all kinds of computing tasks to the data centers. And with all these powerful computing resources, the tasks can be completed very quickly. And also cloud computing is very efficient in the sense that these computing resources in the data centers are fully utilized, right? So all kinds of computing tasks are pushed to the data center to be completed. However, cloud computing is not a solution for all applications. So this is especially true when we send all computational tasks to the cloud. So in that case, our network will be congested and we will have a large communication delay in our network, right? So this communication delay is very important, especially for some emerging applications like those video applications or machine learning and AI, which require intensive computation and also low delay. So people proposed the edge computing in the past few years, which is to perform a substantial amount of computing and storage functions on devices close to end users. So instead of pushing all the computing tasks to the cloud, we can send these tasks to a nearby edge nodes or edge computers, which are more powerful than our end devices. Okay, so in this way, we can greatly reduce the delay over the network. And in the same time, we can process these computation intensive tasks. So edge computing is also not a solution for all applications. It has been a disruptive force for cloud computing, which means that it is complementary to cloud computing. Okay, so both edge computing and cloud computing will coexist in the future, and they have their respective applications. So next, let's look at machine learning and AI, so which are also computation intensive applications, because machine learning and AI use computational analytics of data to achieve artificial intelligence. So what is AI? What is intelligence? Essentially, intelligence is the ability to acquire and apply knowledge. Okay, so AI is viewed as a key methodology for data science, which is also viewed as the fourth paradigm of science. So that means machine learning and AI can be applied as an all-purpose tool to all fields of science, such as physics, such as chemistry, biology, medicine. All fields of science can benefit from machine learning and AI. And this approach is called data science. Okay. So machine learning and AI are made promising nowadays, thanks to recent advances in machine learning methods, especially deep learning, which has been very successful for computer vision. And also nowadays, we have a massive amount of data, which enables machine learning and AI. And needless to say, we have ever-growing computing capabilities, which is necessary to perform machine learning and AI. So real examples of machine learning and AI includes Face ID, including Siri or robotic animals. So machine learning and AI really have a wide range of applications. So here is just a number of fields. So it's really not an exhaustive list of fields where machine learning and AI can apply. So these technologies will bring transformative impacts to different sectors. And more importantly, in many applications, the data used by machine learning and AI are generated from wireless devices. For example, in transportation, the data will be generated by vehicles, right? And in social media, nowadays we access Facebook, Instagram on our smartphones, right? All this data are generated by wireless devices. So I would say a majority of machine learning and AI applications in the future will involve data generated by wireless devices. So when people talk about machine learning nowadays, very often it refers to the inference and the prediction based on a trained machine learning model. Okay, so essentially this is to apply the knowledge which is captured by this trained machine learning model. So in many applications, such as in IoT, Internet of Things, the data used in inference and prediction are generated by wireless devices. For example, if we have a surveillance camera, which can take pictures or videos from the environment, then this image data or video data is used for machine learning inference and prediction. Okay, so usually we can represent a machine learning model, like a neural network model, like this. So this computation task, this inference task, needs to be performed in order to make an inference of what are the objects in this image. So inference and prediction of machine learning needs substantial computing capabilities. So thanks to edge computing, people propose to use to perform these inference tasks at the network edge. That is, we can send these inference tasks, which are computation intensive, to edge devices like a computer server close to the surveillance camera. Then in this way, the network delay can be greatly reduced compared to sending this data to the cloud. However, in order to efficiently perform this so-called edge AI inference, we need to solve several problems. For example, what should be offloaded from the surveillance camera to the edge node? Shall we offload all of the inference task or just part of the task? So if we use a deep neural network as a machine learning model, then we can perhaps partition this model into several chunks and perform some part of the task on this surveillance camera, and then perform the rest at the edge node. Okay, so another possible problem is, where shall we offload this task? Shall we offload to one or multiple edge devices? So all this problem needs to be solved in order to perform edge AI inference in an efficient manner. And in order to solve these problems, we need to be aware of wireless communication channels, because it will determine the wireless communication delay. Also, we need to be aware of the computation capabilities of devices, including the edge nodes and the end devices, such as this surveillance camera. So besides training, besides inference and prediction using a machine learning model, another more important and more complex problem is we need to train a machine learning model in order to perform inference and prediction. So this is the process of acquiring the knowledge. Okay, in order to apply knowledge, we first need to acquire this knowledge. So the training of machine learning model is traditionally carried out in a centralized manner, which means a single computer has all the training data and perform the training on this single device. So sometimes this training can also happen in a distributed manner, usually in data center. For example, different computers in the data center can perform the training of a machine learning model in a distributed manner. But these computers are typically connected by wires. So for the training of machine learning model, it requires much more computing capabilities than inference and prediction. And also we need a large amount of training data in order to achieve a good accuracy for the machine learning model. For example, if we want to train image classification for airplanes, then we may need a large number of photos of which contain airplanes, right? So we may need tens or hundreds, thousands of photos of airplanes in order to train a good, accurate machine learning model, which can accurately recognize airplanes from images. So in order to improve the training of machine learning, people proposed the so-called federated learning back in 2017 by Google. So the idea of federated learning is to train machine learning models in a distributed manner over potentially many devices. So in this way, we can really exploit data from a large number of users or devices as training data, which is needed to achieve a good accuracy of the machine learning model. So this federated learning FL was proposed by Google to as a motivating example for this text prediction application. So I can play this short video here. So this application is to predict the text input by the user on the smartphone. Okay, this is called a Gboard, which is a virtual keyboard on Android smartphones. So here, when you enter one word, the system will automatically predict and prompt the next word you want to input. Okay. So you can see that this text prediction function is really not new. Okay, it has been there for a long time. So when you use Google search, when you type a word, Google search will predict the next words you want to input, right? But what's really new here in federated learning is the way this machine learning model is trained. Okay, so this text prediction is based on machine learning, and this machine learning model is trained by federated learning in the sense that when you input the this text, instead of sending this text to the server in the cloud to train this machine learning model, you train a local model based on your local input data. And then you only send this model instead of the original data to the server, perhaps in the cloud. Okay. As a result, this approach can preserve the privacy of data on local devices. So here in this text prediction example, you don't have to send text you input to the cloud, right? Which may contain sensitive privacy information, right? So that is the privacy motivation of federated learning. So another benefit of federated learning is we don't need to send original data, but just the model to the server, which can have a much smaller size than the original data. So in this way, we can greatly reduce communication costs. So we can see that federated learning would have many applications in wireless networks. Okay, it doesn't have to be in wireless networks, but we can see there are many applications in wireless networks. For example, that text prediction function on smartphones. So in this example, you generate data from your smartphone, which is a wireless device, right? So more generally, for Internet of Things, we can see many use cases where federated learning can be beneficial. Okay? For example, for connected vehicles, we can have different vehicles to train a machine learning model locally, and then send this local model to the server to perform a global model aggregation. So this so-called wireless federated learning, in order to realize it, we need to address several challenges. The first challenge is that devices have heterogeneous local data. So this is a very important challenge because the data on different devices are different. Devices would train different local models. And another challenge in the context of wireless networks is that wireless channels have different channel conditions, and these channel conditions change over time. Okay, so this is due to the complexity of the physical environment and also the mobility of devices. And another challenge for wireless FL is that sometimes devices need to share communication resources due to wireless interference. And therefore, we need to allocate communication resources to different wireless devices. And last but not least, devices can have in general different and time-varying computing resources. So in a typical federated learning model, the server, so it is an iterative algorithm. So the server will first broadcast a global model in each round of the algorithm. Then based on this global model, each user will compute a local model based on its local data. And then each user will communicate this local model to the server. And then the server will collect all the local models computed by users and aggregate these local models as the new global model. And then the next round starts and the whole process will repeat. So this process will repeat iteratively until a desired global model is obtained. So next, let me briefly discuss some research we have done recently on this topic of wireless federated learning. So one idea we have is that we look at the federated learning algorithm. So we observe that in the federated learning algorithm, a very important performance metric is the variance of the local model. And this variance is determined by the mini batch size, which is an important parameter. And this parameter is used when we use stochastic gradient descent in the FL algorithm, which is a very typical algorithm. So this variance is determined by the mini batch size, which is denoted by DTI here. So here GTI is the local stochastic gradient, which determines the local model. So we can see that the variance of this local stochastic gradient GTI is determined by this mini batch size. So a higher mini batch size means a smaller variance, which is better because that will improve the learning accuracy. And learning accuracy is typically quantified by the training loss, which captures how accurate is the trained machine learning model compared to the optimal possible model. So in terms of learning accuracy, we should increase this mini batch size, DTI, right? However, increasing this DTI will increase the computation cost because that means we need to take more samples, take more data samples to compute these gradients. So that means a larger computation time and also higher energy consumption for the computation. So our new idea is to treat this mini batch size as a design parameter in order to control the variances of local models. So in existing works, this mini batch size is treated as a constant, which does not change across devices and over time. So we can see that this mini batch size has a great impacts on not only the learning accuracy, but also the learning cost and the learning time. So due to time limit, let me quickly go through the next couple of slides. So
yes. Oh, go ahead. Sorry. You can go. You can keep going. My bad.
Okay. Yeah. So based on this idea of quality-aware computation for federated learning, recently we have started two problems based on this idea. The first problem is called a cost-effective quality-aware wireless federated learning. So here the idea is to adaptively control the mini batch size based on the device's computation and also communication capabilities, including the wireless channel conditions. Then we find out how mini batch sizes impact the training loss. So specifically, we performed theoretical analysis to find out how the training loss, which is this left-hand side, depends on the mini batch size, which is which is a function of the mini batch size on the right-hand side of this formula. So based on this relationship between training loss and the mini batch size, we study how to design mini batch size optimally and select participating users in the FL process to achieve a good trade-off between learning accuracy and learning cost. And we further extend our study from convex loss functions and synchronous learning algorithms, which are standard settings for FL, to more complex but practical settings, which involve non-convex loss functions and asynchronous learning algorithms. So our results have been recently published in these two papers. So another problem we started recently based on the idea of quality-aware wireless federated learning is to look at the case where devices share limited communication resources. So in this case, different devices need to transmit at different times. So you can see here each block M represents the communication schedule of the corresponding user. So you can see here, these four users have to communicate at different times in order to avoid mutual interference. So in this setup, we look at how to design the mini batch sizes and also schedule the communications among different users in order to achieve a good trade-off between learning accuracy and learning time. So here, learning time is the total work clock time used in this learning process. So this result has also been published in a recent paper. So looking at this area of machine learning and AI in wireless networks, this is really interdisciplinary area. So as you can see, we need really knowledge from different fields, including wireless networks, mobile computing, machine learning, AI, and robotics, and so on. Okay, I think this feature is true for not just my research, but also for research in different departments or different disciplines. Right. I think this is also agrees with the general idea of the Grand Challenge Scholarship Program, which is to really use knowledge in different fields to solve real practical problems. So real practical problem really involves, really has many different aspects and needs to be addressed using expertise from different fields. And here are some future directions, open problems in this general area. So finally, I want to give some final words on my research. So my general research interests are in wireless networks, and my current focuses are, as you have seen, machine learning and AI in wireless networks. And also, it includes edge computing and data cross-sourcing. So if you are interested in working with me, you are welcome to contact me. And here are a few projects I have been working on. So the research results I discussed in today's talk is about quality-aware federated learning in wireless networks, and this is supported by the National Science Foundation. And some other research projects I have been working on include distributed computing in wireless networks. And one interesting hands-on project I have been working with some undergraduate students is machine learning-based mobile robots. So in this project, we install a smartphone onto a mobile robot, which enables this robot to perform a lot of advanced functions based on machine learning and AI. Okay, with that, I want to stop. And thanks for your attention. And I'm happy to take any question you may have.
Yes, we do have a question in the chat. We say we said how can we have floors FL I don't know to say it wrong. Yeah, how can we apply FL in an non-stationary environment?
Yeah, good question. So by non-stationary, do you mean the channel non-stationary? Do you mean the wireless channels? Okay. Yeah. So non-stationary, I assume you mean that this channel do not have a stationary distribution, right? So in that case, I think in our current study, we assume that the channels are known. Okay, the channel conditions are known. So here we make decisions. We design the mini batch sizes and select participating users based on wireless channel conditions. So we assume we know that. Yeah. So of course, sometimes it's hard to predict what will be the channel conditions in the future, but we can predict accurately for the immediate future, right? We don't have to predict information well in advance, right? We can just predict channel conditions in the near future using the current channel conditions.
Okay, awesome. Are there any other questions for Dr. Gong? All right. Well, thank you so much, Dr. Gong. We loved having you speak to us. Yeah, definitely let us know any updates in your research so we can stay up to date.
Yeah, thanks for having me here. I'm very glad to share my research, and I look forward to get more involved in your program if needed. Yeah.
Oh yes, of course. But yes, well, hopefully we can send some researchers your way. But yes, we'd love to collaborate in the future. But yes, hope everybody give Dr. Gong a virtual hand clap. I think we get that. Yes, it is reaction. Yeah.
Thank you.
Yes. Thank you so much for your talk. But yes, I'll let you all go ahead and go. But yes, thank you, Dr. Gong, once again. We loved having you. Hopefully we can have you again. But yes, all right. Everyone have a good evening.
Okay, thank you. Thank you all.